Thank you for your punctuality. How was lunch? Okay, this kind of lame energy means it's been wonderful and you are just a little bit asleep having eaten such great food. But the next speaker is going to energize you as ever. We've had Andreas before. So, you know, there are those code dive speakers. We tried to keep them away, but we can't. And they keep returning. Why am I not surprised? So, Andreas Fertig, he's CEO of Unique Code, and he's an experienced trainer and consultant for C++ standards 11 to 23. He is involved in the C++ standardization committee developing the new standards. He publishes specialist articles and textbooks, of course, on C++. And with C++ Insights, Andreas has created an internationally recognized tool enabling users to understand constructs even better. Previously, he worked for Philips Medicine Systeme as a C++ software developer and architect. And interestingly enough, Andreas' very first C++ book, you'd never guess what it is. He bought it in 1998, and this book still sits on his bookshelf. And the book was Scott Meyer's Effective C++ German edition. Let's have a look, shall we? In case you didn't know, Andreas keeps his books upside down. But this is the one, and again, some people, veterans of Code Dive, may remember Scott Myers was a speaker at this conference as well. So it all falls nicely into place. Ladies and gentlemen, and everyone in between, Andreas Fertig.
Thank you, Raphael. Hello, everyone. I mean, I cannot really see you, but one question first. Who is left-handed? Please, show of hands. All right, because I was wondering whether my upside-down picture came from the fact that I'm left-handed, and I tend to, well, turn the phone different than the right-hand people, and so it might turn up upside down sometimes. But anyways, you can fix that, of course, in software and with C++. Welcome to Code Dive. Welcome to my talk, Fast and Small, C++ When Efficiency Matters. Raphael already introduced me, so there's a little more to say to that. Why do I have the German version of Scott Meyer's C++ book? Because I am German. So that means that I speak German and I can read it perfectly. And at the time, I wasn't very keen about reading things in English. Nowadays, I switched that. My last name is a very German word. It's not really a very German name, but it's a very German word. It's an adjective and it occurs frequently in the language, more often than you think. You can translate it to finished, ready, complete, or completed. So everybody who finished their project basically uses my name. You can use that in other contexts as well. Sometimes it's really hard to distinguish the context. What do you mean, finished or ready, right? The one is the opposite from the other. So if you use just the word fertig, you have to listen very closely at the context to infer whether it means the one or the other. But I guess if you learn German, you know that's sometimes the case and not always very easy. I constantly have a disagreement with my spell checker. It's a very smart thing, so it's right most of the time, except if I sign something and my name shows up, because then in the middle it thinks what I'm trying to say there is Andreas is Fertig, and not that's the name. So it tries to spell it with a lower first letter instead of a capital one, because, yeah, it's an adjective, right? So I couldn't teach it to do that any better in the past. But we are not here, or at least I'm not here to give you a German lesson. I'm not really a good German speaker, despite I'm German. I think I'm best in C++ grammar, not even an English one. And we are here to talk about fast and small software, right? Because this is important. I worked a lot in embedded software development for my career before I started training and consulting, but I still do a lot of these domains. And usually you have devices that are somehow constrained, and constraints can be that you have a physically very tiny device, but also in terms of memory resources or CPUs. So you might have to squeeze a lot of functionality in only a few kilobytes of RAM or ROM, so you want it to be small. But on the other hand, you might have timing constraints, and you cannot lose your edge there, so you have to be fast. And in my experience, it's usually the one or the other. You have rare times when you can win both to your favor. So today I like to present you a couple of techniques, things I saw, where you can try to achieve either faster or smaller software in C++. So the first thing here comes from the standard library. What you're seeing on this slide is hopefully something that you already used extensively. It's a declaration of a unique pointer object f. And that unique pointer, it maintains a file type. And I'm working a lot with Unix, Linux, so I use POSIX API here, and that's a very good example. If I do a fopen to open a file, I get back, sadly for presentation, an object named file. So the type of that thing is also called file because it was easy, I guess. And what I'm doing here is I used a less frequent version of a unique pointer, at least to what I see on daily basis. And this is that I provide a custom deleter to my unique pointer. So this is why you're seeing a unique pointer version here with two types instead of the usual one. The first one is the type of what the unique pointer here wraps, so my pointer type. And the second one is some callable that's invoked instead of delete when the unique pointer gets destroyed. Okay, and this helps me that I can have a fopen returned object wrapped in a unique pointer such that once I'm leaving scope, the file is automatically closed, which is a very nice thing to keep your resources safe and let the infrastructure maintain it automatically. Now, to achieve that, I not only have to provide a second parameter to the unique pointers templates parameters, I also have to provide a second parameter to the constructor, telling it or teaching it that the function we are talking about is called fclose. So I pass in a function pointer to that. And it works perfectly. I'm happy with that. I have a safely maintained resource here. That's perfect. But how about efficiency? So what's the size of this unique pointer now? We aim to say a unique pointer is just a simple wrapper around the raw pointer, so a unique pointer size should be equal to a pointer size, right? I think we still have a few of these unpleasant spots in the front if you want to join. I personally don't like them either, unless I'm on stage, but feel free, there are a few left. So if we check out that unique pointer size with, let's say, a static assert, in my particular case, it turns out that the size of this object f is greater than the size of a void star. So this unique pointer version here, it, in this specific case, has twice the size of a pointer. Because internally, the way I've written it, we have, or the unique pointer has to store two pointers. One for the actual data, and another one for the function to call in the case we want to destroy it. That's fine. There are use cases when this really is all right, but in this example, I beg to differ. Because I'm calling a function fclose, there is no real runtime-ish thing going on where I have to decide which actual function I want to call upon destruction. It's fclose, and the address of fclose is known at latest as link time. So I have the address. Why store it in a pointer and not only waste storage space, but also have this indirection and store the address? It's little, but it's a waste of resources. So what can we do there? Let's first start saying that in the way I use the unique pointer here, the second parameter, it's always there. If you don't provide any, the infrastructure, the standard library here, uses something that's called a default deleter or default delete, which, as I present here, is a class template with only one member function, and that's a call operator. That one takes a t star. The t comes from the template parameter, and internally it simply calls delete on the parameter that gets passed to. So whenever you use a unique pointer with just one template parameter, it always does this trick, at least in most of the implementations. So it never calls delete directly, it always goes over this default delete. So that's one piece of that. Now, how does the implementation of a unique pointer look like? A unique pointer's implementation can look like that. It's a reduced version based on more or less libc++. And it takes, well, no surprise, a class t, that's my first template parameter, and the second one, I call that one del here for deleter, and that one gets defaulted with the struct I just showed you, default delete of t. Now, if we start looking down in A here, we can see that in this instance here, my unique pointer does not directly store two pointers. It stores, or it creates an object called compressed pair, and that one is typed with del and t star. And then we have the regular functions here, the constructors in B and C, so the one for one argument, constructing just a unique pointer with the default deleter, and a unique pointer with two arguments for the pointer and a custom deleter. And in each of these two cases, the data is simply passed forward to Ampere. So Ampere is the next thing we will look at. If we stay with the unique pointer, we can see it does the usual thing, right? It's not copyable, so the copy operations are deleted. It's only movable, so I implemented them here. And if you look down to D in the destructor, then it's, I think, worth to know that compressed pair is a utility class used frequently in the standard library. It's not just for the single case of unique pointer. And that's the reason why, if you look at the unique pointer, it might look very odd, because the check here now in the destructor of unique pointer is checking whether ampere.second returns false. So it's comparing a pointer or observing some Boolean value. And if that's true, then we are invoking ampere's first with ampere's second. So you could say ampere.pointer. So this is the check. If that's not a null pointer, then let's invoke ampere.delete with ampere.pointer. That's essentially what the code here does. Now, the compressed pair is this one here. And I had a hard time to decide which code to show you. I decided to go for the C++20 implementation because it fits nicely on one slide. The pre-C++20 solution would not have fit in one slide. So upgrade to C++20 if you can. What you can do in C++20 to make this code so small, so tiny, is to say, okay, compressed pair here, I think that was obvious from the slide before. It's a class template. It takes a deleter and a type name t. I used more proper names here. And then compressed pair comes with two member functions, first and second. First being of type del and second being of type t. And I'm using an attribute here that was introduced with C++20, no unique address. And what this attribute means is if the object del.t is empty, there is no requirement on your compiler to allocate storage space for this object. So you might have heard of a similar technique that was present long before C++20, EBO, the empty base class optimization, which roughly says if you have a class with no non-static data members, so you can have member functions in there, but you cannot have member variables that are not static, then your class basically occupies 0 storage space. But the moment you start asking it with size of, hey, are you 0? Your compiler says, well, the size of this struct is 1, at least 1. Because everything in C and C++ must be addressable. And to have an address to something, you need at least the size of 1. So EBO says, if your object has technically the size of 0, and you use this data type and derive from it with another data type, then the second data type size is just its own size, and the size of the base class does not contribute to the size because that one is 0. And this is the reason why the pre-C++20 solution would not have fitted in one slide, because I would have a lot of inheritance going on there. With the no unique address, you basically have this optimization on your hand. You no longer need the inheritance step to do. You can simply say, I'm interested in this type and the features of this type, in this case being the member functions. And no data members are required for me here. But I also don't want to do the inheritance dance because I don't want to model any is a variant or whatever. So no unique address here basically says if any of these types has the technical size of 0, so no non-static data members, it will not occupy any space in this structure. Remember the custom delete I showed you? The only thing it came with was a single member function, a call operator that invoked delete. So it had the size of 0. So that was the first thing that fulfilled this requirement. And that means that in my case here, the data structure first member, it does not occupy any storage space in the structure. My pointer, T, second, yeah, that will take up the size of a pointer, of course. Somewhere I have to store the information. And then I have the two constructors here, my compressed pair with one argument and with two arguments, initializing the two data members. And with that, you have that efficient tool in your hand that you can say, if you have data that you want to wrap somewhere where you're only interested in member functions and not in the data, but you do not want to store a pointer to that thing because you always only use these member functions, you can tag them with no unique pointer. And then it will not occupy any storage space. Or pre-C++20, do the dance with the inheritance and have an empty base class. So this is the heart of everything here, the compressed pair, because that one ensures that the custom deleter does not occupy any storage space. In the default case, right? Because the version I showed you, the static assert, still proved that it occupied storage space. So let's optimize that one. We can write a better version of this delete with a custom deleter for a file object than I showed you initially. And I'm continuing to use C++20. This is a utility that I like a lot. You can call it better. Maybe I refer to it as unique pointer deleter. So it's a unique pointer with a custom deleter. It's a using alias that's a template at the same time. So it comes with a template head. It takes a type named T and a C++17 non-type template auto parameter. Call that one delete fn. So that's my function pointer that gets invoked and deletes everything or frees everything, closes everything, whatever the action behind this is. And my unique pointer deleter, it's a using alias pointing to a std unique pointer of type T. And now the magic happens. The second parameter, my custom deleter, as I said, I'm using C++20 code here. So that one uses a decal type on a capitalized lambda. Because in C++20 you can decal type on a capitalized lambda. Decal type on unevaluated or have a lambda used in unevaluated context. And because it doesn't capture anything, it's not used or it can be used in that context. At the same time, because it doesn't capture anything, if you remember how lambdas work, internally they are just classes, and our captures are data members, and the call operator is a member function. Since I do not have any captures, I do not have any data members in this class. So I only have member variables, or member functions. And exactly one in this case, and that's the call operator. So this lambda here that does the same thing as the default delete that I showed you, it's basically an empty class with just one member function. And my member function here takes a t star, I call that parameter ob, and then internally I invoke deletefn with this pointer parameter ob. So that's totally transparent to everything. It can take everything that's invocable. And my usage here then is that I say unique pointer deleter of file of fclose. So I teach that thing the function I want to have it to invoke upon destruction. But my constructor just takes a single argument as usual. So I find that syntax way nicer because my users do not have to pass 2 arguments to their constructor, which seems odd somehow. And I do not have to repeat myself because I say fclose only once. That's the thing I want to invoke upon destruction. And now if you look at the static assert here, you can see if I check now whether the size of this object f is now equal to a void star, that static assert passes because I employ the same trick as the standard library does it by default with the default delete. So this is how you can optimize code where you use a custom deleter, but your pointer is basically, or the function that you want to invoke is known at compile time. Okay? Before, I added the size of one pointer to each instance of this unique pointer object. Now I reduced it. So you can see it either way. Maybe you just reduced your code by 50%. It's a good measure, right? Maybe don't tell your manager it's only about 8 bytes or so, but 50% is a better sales pitch. It's all about sales, even in programming. Can we do better? If you really want to squeeze out the last few, let's say, instructions, can we do better? There's still something that we can say it's not perfect. Remember how lambdas work? Lambdas are class type. They have this call operator that then gets invoked when we invoke the lambda. And since they're a class type and we have this call operator, a call operator is a member function, right? What do you know about member functions? The implicit things. The this pointer. Each member function in C++ takes this implicit first argument, the this pointer. And in C++23, we call it the implicit or explicit object parameter thanks to deducing this. But there is one parameter that this function always takes, and we know it's useless because there are no data members inside this class, so there's nothing that we would access with the this pointer. In C++23 now, you can do one thing better. You can mark your lambda static. That means that the call operator of this lambda is now static, and it has the same implications as if you make any other member function a static member function, that it does not come with the implicit this pointer. And by that, you are squeezing out 1 to 3 assembly instructions because the this pointer has not to be prepared and not to be passed. It depends on your architecture and usage. But this is what you can do on top if you have C++23 on your hands. It's not required to, or it doesn't work only on lambdas. You can put it on every call operator or every array index operator in C++23, but on lambdas alongside them. So that's an optimization you can do there. All right, so we had unique pointer. Are you using the standard library? Just by a small show of hands, as I said, I can't see a lot. Thank you. All right. Seems a lot of you. So you might use std string. and you might have heard of the small string optimization. So if you're looking at a std string, at some point we decided that allocating just a single byte from the heap might be somewhat of an overhead, and doing that frequently. So we looked for better techniques, and the one that's present currently is called the small string optimization. And that means that for a certain size of small characters, so let's say 16 or less, we do not go to the heap, we store them on the stack. So every std string object comes with some internal array which then lives on the stack. So if we are about to design such a string class, we can say, okay, we know that we need the size to be stored. So how many characters are currently in that string? We also need the capacity, because that's how many data can be stored there totally before we exhaust the dynamic memory and have to reallocate. Of course, we need a pointer to the data, and since we want to implement a small string optimization, we need something like a car array, let's call it MFSSO buff, with the size of, let's say, 16. And now, since we introduced two modes to our std string, small or large, we need to store the information in which mode we are operating somewhere. So let's add the boolean to that, let's call it MISSSO, and say by default it's true, we start always in small string mode. So we carefully design that, and if you look at the static assert, that nice little structure consumes 48 bytes, which is a lot, given that we tried to optimize for the small bytes, right, for just a few characters. One reason that it consumes that much storage is the so-called padding. So if you ever heard about that or haven't, C++ Insights can visualize that. If you look here and turn on the show padding information and then do the transformation, C++ Insights tries to show you nicely that this structure here is size of 48. It's aligned at an 8-bit boundary, 8-bit boundary, and and here is where all the stuff starts. And then we can see it ends with 7 bytes of padding. And this is because we squeezed in the 16-byte buffer and then a single boolean, making that not really well padded. 7 bytes wasted in some of the embedded systems I worked with, that's a lot. That's a good fraction of the entire storage space that was available. So it doesn't seem the best to do it like that. So what I'm going to present is a short version of what the standard libraries do. Okay, so it's not my work, it's also a reduced one. The first one here is libstd.c++, that's Clang's standard library. They say they have this structure and they store a pointer first and then a size. So that's what we worked out, right? But then they use a union, because they say at one point we only need the capacity or our small string buffer. And to make all the implementations look similar, I decreased the size of the small string buffer here. I'm using 8. The real capacity is larger, it's more 16. So they say we only need the one or the other, because we are either in small string or medium string mode. The entire structure here now consumes 24 bytes, so that's way better than before, but we only have 8 bytes for small string optimization. Then we have a couple of recurring functions here, maxcap, that tells you how many characters you can store in total. That's simply the size t's capacity. SSO capacity tells you how many bytes or characters can be stored in small string mode, and that's my SSO buffer capacity and buff -1, because we have to store the null terminator somewhere. So in this case, we can store 7 bytes of payload. And then we have a function to check whether it fits into SSO. And the next function is where they do the trick. Is_long. So is_long answers the question, are we in small or large mode? And what they do here is to say, we check whether pointer points to mbuf, so it has the same address, or not. If it's a different address, we are in long string mode. If it's the same address, we are in small string mode. So this is how they removed the Boolean. They have this information already stored somewhere. Then we have the constructors for default construction constructs a small string. We have a constructor taking a const star and a size t. That one checks whether the string fits into SSO. If so, it initializes mptr with mbuf. Otherwise, it will allocate dynamic memory. And then it has to check again, are we in long mode? Then we have to update the capacity, and finally would copy the bytes over, of course. Now, size and data in this implementation are now simple. They simply return the member functions, but capacity comes with a branch, because capacity now has to check whether it's in long or in small string mode. So this is where you're paying for. This is the check that has to be done. As I said, this is GCC's implementation. This here is Microsoft's implementation for the Microsoft standard library. They start differently. They say, well, we have this union and we decided that we only need mpointer or mbuffer. So it's nearly the same implementation, but they play the trick differently. And after that, they have size and capacity. This structure also sums up to 24 bytes. Their SSO capacity is also whatever size t gives you. SSO capacity itself is 7 bytes as previously. And in is_long, they are now checking whether the capacity exceeds the small string capacity. So this is how they store the information. They say we are using capacity all the time, but once we know the capacity exceeds SSO, we are in long string mode. Otherwise, we are in small string mode. Now, in their constructors, they start with small string in default construction. They, in the 2-argument conversion, they initialize mbuf here to give the union a defined member. Then they initialize size with the length. For capacity, they check whether it fits into SSO or not. If it fits, they initialize that one with the SSO capacity. Otherwise, with the length we have. Next, in the constructor's body, dynamic memory will get allocated in long string mode and data will be copied over. This implementation here now makes it easy to access size and capacity, but it comes with a penalty on data, because data now requires the branch, because we don't know whether we return pointer or a pointer to the small string buffer. So we squeezed the two together, but now we have penalties there. And this is something where you also have to check what you want to optimize for. Is data a fast path that needs to come out without branches, or are the others better? I personally don't know. I'm just showing you the implementations. I assume they measured and came up with a good idea. Now, the third implementation here, it's the newest among all of them. It comes from Clang, so it's Clang's standard library, libc++. And for all the quick readers here, you can see the last part on the slides says to be continued. So this is the first implementation that even in the reduced form doesn't fit on the slide anymore, because they are doing real interesting things. I like these bit fiddling things. I've done that a lot, and they are doing it. So what they do, they basically start out and say, we have two structures. Let's call the first one normal. And normal contains a size t large, a size t capacity, but they're bit fields. My large member is a bit field of exactly 1 bit, but of type size t. And capacity is a bit field of the size of a size t minus 1 bit, because we just spend that on large. And then we have a regular size t size and a pointer data. SSO, the other structure, that one says we have a single bit here for large, and followed by that a array, another bit field of uint 8t, which has the size of uint 8t minus 1 bit. And then we have a couple of padding bytes in there, followed by data. And data has the size of normal minus the size of a size t. So that data here has 16 bytes of payload. Minus 1, as we will see on the next slide, for the null terminator. We pack the two in a union. We say we have small and large. The total size here is still 24 byte. And max capacity now is a reduced version because we did the bit fiddling. SSO capacity is the capacity of SSO data, so 16 bytes minus 1 for the null terminator, fits into SSO, and all the rest you've already seen. So this is their implementation. This is the one which gives you, even in the real world implementation, the most amount of small string capacity. But you're paying for that because if you look down to size, data, and capacity, now each and every of them comes with a branch because we have two unions and we never know in which state we are. So more SSO capacity, but maybe more branches. It's your decision, basically, what you want to optimize for. But this is what the implementations do. So this is enough standard library, right? Let's talk about something else, Constexpr. Jason Turner does a talk later about Constexpr, so go and watch that one. Here's one slide for me. This comes from a client. I had a consulting job there. They called and said they're close to the release and they're running out of memory. So they wanted some help to reduce the memory consumption. And I was looking at the code and I figured out that the device, it was a small device, networked, and it basically passed around strings. Call it a string distributor. No offense. And the heart of everything was a class called fixed string, something maybe similar we are getting in C++ 26. It comes with a non-type template parameter n, and this gives the size of an array that's stored inside fixed string of type char here, and the fixed string class also comes with a size t for m size, so we are carrying around the size. Then we have a default constructor. We have a constructor that takes a const char star, figures out the length, and copies everything into its internal buffer. There is a function size, and there's a function data, which grabs the data out again. And this was extensively used. They had two basic usages. One you can see in line 24. That was their first attempt. They said, okay, developers, let's use that fixed string class, and they make the mistake to tell them count the length of their string. I mean, who wants to count the length of characters, right? We are developers. So most of them sat down and said, yeah, 50, some 48, because it's such a round number. That should be enough. Okay, my string fits in, everything compiles, it's nice. They updated that and said, okay, we squeeze in another function called make fixed string. That one uses template tricks to deduce the size of a fixed buffer and instantiate fixed string with a perfectly matching number. So the second one is obviously the better one. And as I show it, the two static variables here, x and y, they were static and const already. But when I came in, I figured that one out after a while and asked, why not make it Constexpr? And they told me, because it will not change a thing. It's already static, it's already const. What will Constexpr do? I was on their budget, so I had a little fight to get the time to add Constexpr to like 10-ish places or so. And this here is Compile Explorer. I assume you all know Compile Explorer. And this time it's a 3 window version. On the left, we have the fixed string class. That one here has Constexpr in capital letters here all over the place, so that indicates a macro, right? And I made the two variables Constexpr as well. And then I have two compiler runs here. The one in the middle, that one is the original version, so I'm using C++20. I define Constexpr to nothing, and I use 0. And the one on the right, that one defines Constexpr to really be Constexpr. Now, if you look at the original version, that one comes up with 209 lines of assembly instructions. There are a few blank lines that Compiler Explorer inserts, but let's ignore them. My Constexpr version comes up with, oh, beautiful, 78. So it did cost me less time to add the annotations there than fight over the budget. And it's already way down. But they didn't compile with 0, right? So let's be fair and realistic. In 03, the original version uses 42 lines of assembly instructions. That's way better. The Constexpr version, 31. Well, still better, but not that good, comparing assembly instructions wise, right? The main difference here comes solely from this piece of assembly instructions. What that thing does is it initializes your static data. It initializes your static objects, calls the constructors. So what happens here is real bad, because what's happening here is that the machinery says, oh, we have this string in the ROM, and now let's spend time and stack space and copy it from ROM to RAM to make it accessible to you. So this 10 instructions difference, it's a big difference. It consumes stack space and it consumes your runtime. Okay? This is not present in the right compiler run, because there is no reason to run a constructor at runtime. Look at this, because the compiler here perfectly understands the layout of my object. It already has it there. It can tell in assembly, that's your object X, and the first part of this object, this is the size, it's 22, followed by the string, followed by padding, because the developer simply said 50 bytes, followed by another padding because fixed string structure isn't perfectly aligned. And the same thing for Y, just with one padding, because that one is perfectly trimmed to the size of the string. So while we only have 10 lines of difference in assembly code here, the left-hand version is slower at startup, and it consumes your precious RAM, stack space at runtime. So this is what Constexpr can do for you. This comes from a real-world example. At least at the moment, I cannot do any better on telling you Constexpr is really worth it. And if you still believe me, and even if you do, go and watch Jason's talk later. Okay? So I hope you had fun. I could tell you some things that you haven't heard before. And before I think we have a microphone here and open for questions, let me say I had fun. Thank you. I'm Fertig. Thank you.
Thank you. Thank you so much, Andreas. And I think we've got if you'd be so kind, time for 1 or 2 questions. So questions, please. One over there in the second row, please.
Yeah, thank you for the talk. I wonder about memory utilization, but the compiled code. I think it was on slide number 8 where you showed how to wrap a lambda. Use a lambda to wrap the deleter. And I believe, oh yes, here.
That one?
Yes, so there's a lambda in line 3, and I believe it will always create a function in the final binary. And that function, the only thing that it does is to forward to the actual function. So can we do any better? Do we need to pay that price?
I think we, at least to my knowledge, cannot do any better. Your optimizer might do, but you have to invoke that thing at some point. The only other option you have is, but that would eliminate that use case, to say you have two different versions of unique pointer. So a specialization, one that only takes one parameter and the other one that takes two. But with a custom deleter, you still have to store that information somewhere. So your optimizer might be able to peel off the first layer, but I'm not sure.
Okay, so if it's worth the extra step, then we can provide this specialization if needed.
Yeah, if you implement a unique pointer yourself, then yes, you could think about providing a specialization instead of packing everything in one implementation, but you would pay a different price. So question is, which one is the better for you?
Thank you.
You're welcome.
Thank you so much. Any more questions, please? One over there, thank you.
Actually, I wanted to ask the same thing. However, I have kind of an idea how to do this. Basically, I guess you could specialize, write a specialization for the template for function pointers, because you can make a template argument as a function pointer, and then the address itself is like kind of baked into the unique pointer type, and then you can skip the...
So you would basically say use this as the template head for a specialization of unique pointer. Your delete fn carries the information for...
So you can either have like a general version of the template where the delete function is anything that can be called, for example, a lambda, or a specialization for function pointer explicitly.
Yeah.
And then skip the...
Yeah, you can do that. That's what I said. It's a question what you're optimizing for, because now you have twice the code to maintain.
Okay, lovely, thank you. Perhaps one more? Any more questions, please? First row, please, thank you.
Yeah, hi. So on one of the slides you showed the Clang's implementation of the short string, right? And there were a line where the union access was indiscriminately accessed. Isn't that undefined behavior in C++ to access non-active union member? Or is there any exception in the standard that allows that? I believe it was this is large method.
So you're talking about this here, and basically the straightforward access in is long to packed small that large, right?
Yes.
And you phrased that question so great for me just to answer, yes, there is special wording for these circumstances in the standard, not for std string, but in case if you're interested, I'm not sure I can bring that one up here. The section in the standard you're looking for, I'm failing to do that. Wanted to show you. Okay, it doesn't work. The section in the standard you're looking for is class.mem.general, and you want to basically look at paragraph 28, and I've written that down. I'm not knowing that from the top of my head. This talks about the common initialized sequence. And the reduced version, and turn the internet off for that answer, is if you happen to have two types that are coming without constructors and destructors, so just a bunch of bytes, and they have the same signedness and the same length of bits, it doesn't matter which one you're accessing.
Okay, so generally, if I am sure that this is well-defined access, I can do that without violating the undefined behavior that otherwise could be invoked here.
Yes, there is no UB here, but if you do this at home or at work, be really careful to understand the rules, because it only works in exactly such scenarios.
Okay, thank you.
You're welcome.
Thank you so much, Andreas. Thank you so much for your talk. Thank you for answering the questions, and you are now officially done. Everybody, Andreas Fertig.
Thank you. Thank you.